Hello, Steve Stufflettle from Erie Community College here. This is a follow-up video or a continuation of a previous video where we talked about assessing the print quality for a laboratory project using the rubric. In that previous video we talked about the mechanical features of a print, which would be the in-feed register and the side guide register, and we were looking for obvious visual defects like blanks from double sheets at the feeder or ketchup dry up at the gripper. This analysis is about the color variation or the density variation. So what we talked about previously was taking a random sample or an interval sample and measuring the solid ink densities, or SID/SIDs. So if you recall, we have solid areas where we can measure the magenta here, the yellow here, the cyan here, and the black here. Now, just so you know, I typically try to, when I do an analysis in Excel, I leave one tab for introduction, and then I use descriptive names in my tabs here. So let's go right to the data analysis. So I had two labs. I had a Monday morning lab and I had a Tuesday afternoon lab. We ran 3,000 press sheets for the black. That was a preprint. Then we split that 3,000 in half. 1,500 ran on a Monday and the other 1,500 ran on a Tuesday. From that, I pulled 10 samples at equal intervals. I believe that was about a ½ inch, 0.5 inches, which for a 60-pound offset is about 111 sheets per sample. So we numbered the samples 1 through 10, and we measured the cyan, magenta, yellow, black densities. We then did some very basic descriptive statistics. We measured the maximum or the highest. We measured the minimum or the lowest. From those two, we subtracted them to get a range. A range is a distance measurement, but we have to be careful about the range because the range is very sensitive to extreme outliers, so there's got to be a better metric than the range, and there is. That's the standard deviation. So the standard deviation, or sigma as you hear it pronounced, is the amount of variation in a process. And then of course we could calculate an average, arithmetic average, which is also called a mean, not to be confused with a median, the middle, 50%, or the mode, the most occurring. So now that I have the average of 121 for the cyan, an average of 118 for the magenta, an average of 87 for the yellow, and an average of 111 for the black, we can compare those against the target aims. But realize that these target aims are for wet densities, not dry densities. So once I know what my target aim is, and once I know what my average is, I can compare those, find a difference, subtract them, and that difference is my accuracy. So in the case of cyan, it ran at an average density of 121. It was supposed to run to a target of 110, which means it was plus or 11 points strong or darker. The magenta was 8 points darker. The yellow was 3 points lighter. The black was 14 points lighter. Now let's talk about the black for a second, because if the aim for black is 125 wet, fresh, we know that black is going to dry back a lot. So how much will black dry back? Well, from a previous, I don't see it here. From a previous data analysis, we know that the dry back is about 15 points. So if I compare 111 to 125, I'm 14 points light. But if I change this to 110, knowing it's going to dry back 15 points, my accuracy now is only off by 1 point. So I think I'll do that here because we know that that's going to happen. Okay. So the number we really want to talk about here is that standard deviation. The question now becomes, how much standard deviation do we have, and what does that mean? So the lower the number, the less variation there is. The higher the number, the more variation there is. Now, a couple interesting points here is the black has the same standard deviation on both the Monday and the Tuesday class because the black was pre-printed the week before, prior, and it ran all 3,000 sheets at once. The Monday class had a cyan standard deviation of 17, but the Tuesday class only had a standard deviation of 6 on the cyan. So that's about 3 times better. Looking at the yellow on Tuesday versus the yellow on Monday, again, 2 versus 6, this is about 3 times better or less variation. Now, of course, the level of operator skill, the knowledge and the experience they have is going to affect the performance outcome and results. So you could say that this was a material dependent result or a process dependent result or an operator dependent result, probably mostly because of the operator. Okay, so now we know the accuracy and we know the standard deviation, and I use that in consideration for grading your grade using the rubric. All right, let me see if I can get to another slide here. Just a second. Okay, this is a different Microsoft Excel spreadsheet. Again, I always try to give you an introduction sheet, a miscellaneous notes sheet, and if you want to read these at your leisure, you can just pause the video to give you more time to look at them, and then I go to the raw data. What this graph is telling me is I measured the density after several minutes. So at 0 minutes, the ink was fresh and wet right out of delivery. And then a minute later, I measured it, got 137, so it dropped 3 points. 2 minutes later, I measured it, its density was 136, so it dropped 4 points. 3 minutes later, I measured its density at 135. That means it dropped 5 points total. And then we went to 105 minutes, which is, an hour and a half or more. And after an hour and a half or 105 minutes, the black dried back or dried down 15 points. So if you take this raw data, which in tabular format, rows and columns may not be that informative, and now you visualize it with a graph or a chart, you plot it out, you can see that this curve is typical for ink dryback. So immediately right out of delivery, when the ink is wet and fresh, it has a higher density, but over time it dries back or dries down. Now most of the dry back occurs quickly within the first 5, 10, 15 minutes, and then slowly it becomes more gradual. Now you could argue I should have went a little farther here because it doesn't look like this exactly flattened out or plateaued out. Now this analysis is only for black ink on uncoated paper. My recollection is that if this was on coated paper, the dry back for cyan would be about 3 points. The dry back for magenta might be 5 points. The dry back for yellow is minimum, only maybe 1.2 at the most. But the black dry back is the most, typically 10, 15 points. Okay, so that tells us more about dry back. Let me go to another spreadsheet here. Now, again, I always try to put a introduction tab and a miscellaneous notes tab in my Microsoft Excel analysis to remind me and refresh my memory about what the purpose of the experiment was, how was it conducted, what were the conditions, things like that. So in this analysis, we did this back on 3/26 of 2019. It was also the Bunny Rabbit project. And what we did is we ran almost 500 sheets. And I measured the density consecutively, one sheet after the other, right? So what we found out here was that the standard deviation for running almost 500 sheets consecutively in a row and measuring every sheet was 0.038. So this kind of provides you with a reference or a baseline or a benchmark to compare past, present, and future analysis. So you might want to write that number down or recall it, because that might become useful later. And then another analysis that we did in Excel, well, actually this is not analysis, this is an attempt to help us better understand what standard deviation is. So here is what we refer to as the normal bell-shaped curve. The technical name would be the Gaussian distribution. So what I can do here is I can change the standard deviation and the means. So if I change the mean, let's make these means and standard deviations the same. When you do that, obviously these two plots and graphs are going to superimpose on top of each other. Okay. Now if I shift the average over by one mean, you can see I shifted to the right. If I put a -1 in here, you can see it's going to shift to the left. So the mean, or the average, only tells you about the centering or the location or the position of your distribution. Okay, let's get these to be the same again. Now what I want to do is, relative one to the other, change the standard deviation. So here the standard deviation is 0.33. If I take this and make it smaller, 0.1, you see that it becomes tighter, which means it has less variation. It becomes more like a mountain peak or a spike, right? If I make it wider, it has more variation. So if you recall, we had in the 500 consecutive press sheets, 0.038 excuse me, was the standard deviation. I think when we ran the black preprints, the standard deviation was 0.08. Okay, those numbers are pretty tight. You can see the variation here. I just have to zoom it out differently. Let's do this, 0.33, 0.11. And again, you can see that the shape is always the same. It's a normal bell curve. It just changes in the width of the base, the range here, the dispersion, the variation, the standard deviation, but in this case it's always the same average or mean, the location or position. So I don't know, this may be slightly relevant. We have the coronavirus COVID-19 global pandemic, and they keep talking about flattening the curve. What they're trying to talk about is from going from a typical distribution, if you don't take any preventative corrective action, flattening curve means trying to bring this down, which means it has less effect when it comes to healthcare services. You're not overwhelming the hospitals. So if there was a horizontal line here that was the capability or the volume of hospital beds for treatment, you certainly don't want to exceed that. You want to stay below it, which is what they mean by the flattening of the curve. Okay, finally, what we can do now is go to another analysis. Now, we'll do this when we have an opportunity, but I've been doing this, I think, for the last 8 years. What I have students do is take 5 nickels, coin nickels, weigh them on a digital scale, and record the year stamped on the coin and record the weight measured in grams. And I have over 233 data points for this. And again, we can calculate maximum, minimum, range, an average, and a standard deviation. And what we do here is we plot these on a graph, so we can take a look at this. Let me drop down just a little bit here. So you can see that this is the year the coin was minted, and this is the weight in grams. So what's interesting to me is it looks like from 1950 to almost 1970 there was this one population of coins, and then from 1970 to about 1990 it looks like there was this other population of coins, all of them being on the heavy side in terms of weight. And then it looks like from 1990 to current 2020 that these coins were more evenly or equally distributed on the heavy side or the light side. So this is often called an XY scatter diagram or a plot. Now let's take the same data and look at it slightly differently. We can take a look at a histogram, and a histogram is nothing more than a vertical bar chart, and what we're looking at here is the values versus their frequency of occurrence expressed as a percentage. So what this histogram is telling me is that if the target aim weight of a nickel coin is supposed to be 5 grams, and it is, we only had 8% of all the coins with that weight. Now, as most things in nature occur, they have a normal bell-shaped Gaussian distribution. Nothing can ever be exactly perfectly the same all the time. Things are going to vary. So we see that the variation happens in terms of a plus or minus, above or below, more or less, higher or lower, lighter or darker kind of a thing. So here the coin weights are getting heavier to the right. Here the coin weights are getting lighter to the left. So again, we have our normal bell-shaped distribution, but it's slightly skewed. It has this longer tail to the right here. So I know a lot of the students aren't comfortable with mathematics or statistics, but you've seen that in Lithopress 1, Lithopress 2, and then next semester in Lithopress 3, we just can't get away from the mathematics, right? And when it comes to quality control, QC, or quality assurance, QA, in the old days we used to call that SPC, statistical process control. Today, currently, we call it Six Sigma or lean manufacturing. Whenever you have data, you should make measurements. Well, excuse me, it's the other way around. Whenever you have a process, that process has an output. We should measure the output. That gives you data. From the data, we should do some type of analysis, and that analysis of the data will give you new information that's actionable, corrective action, process improvement, continuous improvement, often referred to as CI. So I guess the point I'm trying to make here is you really need to understand what a standard deviation is, the amount of variation in a process. The lower the number, the better. The higher the number, typically the worse. And whenever there's output and wherever there's measurement, there's data, and that data should have some analysis. Okay, so hopefully this wasn't too advanced or too technical or too difficult or complex for your understanding or comprehension. The advantage of having these videos is that you can replay these back maybe a second time or a third time over and over again until those subtle points that I'm trying to make are well understood. Okay, so let me just go back to the original analysis, which was we measured magenta, yellow, cyan, black densities. From that data, we calculated a standard deviation. From the standard deviation, we can conclude if it was good or bad. We know when it comes to wet, fresh ink films that when they dry over time, they will dry back or dry down. We know from a previous experiment about a year ago in 2019, where we ran 500 consecutive sheets, that the standard deviation for 500 consecutive sheets was about 0.38. And we saw what it means when you change the standard deviations and we also took that concept or principle and we applied it to measuring the weight of coins. So we had a XY scatter plot diagram showing us how these were distributed. And then we also took that data and we put it into a histogram. A histogram is nothing more than a vertical bar chart that shows you how the values are distributed. Footnote here, the reason why you should know what a histogram is because in Adobe Photoshop and in digital photography, you get a histogram. And the histogram would be the pixel gray level value versus its frequency. So the pixel, if it's an 8-bit pixel, would have a minimum lowest value of 0, which is black, and it would have a maximum highest value of 255, which is white. So half of 256 is 128. So if your pixel value was 128, it would be a medium middle gray. So having a histogram in Adobe Photoshop helps you understand the exposure level of the original digital photograph, plus how you should edit that photograph for color correction if you use tools like levels or curves and the threshold command to make a bitmap image. Okay, so we'll talk to you soon. Have a good day. Bye now.